Hey, hi folks. I'm Pete Delvecchio. I'm the product line manager for the Tomahawk family. I've also been with Broadcom for a long time, not as long as Mohan, but actually started Broadcom, before the first Tomahawk chip. And I remember when 3.2 terabits per second, which was the first, Tomahawk chip, seemed like an insane amount of bandwidth. But today we're at 51.p, and we see that continuing in the future. Today I'll be talking about two topics. One is AI interconnect. I mean, I love congestion control and load balancing as much as the next person, maybe not as much as Mohan. But one thing is that the first thing you need to do is be able to like physically interconnect the AI devices, the switches, the NICs, the GPUs, etc. So we actually spend a lot of time trying to improve the physical interconnect between the devices. And this AI interconnect, this applies both to the Jericho solution and to the Tomahawk solution that I'll be talking about in the second part of this presentation. Okay, so agenda for today. First off, talk about the AI physical interconnect, get into a high-level discussion of the Tomahawk AI cluster architecture, and then talk about some of the features that we put in the Tomahawk switches to support the cluster architecture based on this silicon, including the very high bandwidth and high radix, and talk about why that's important, how it benefits you as far as latency, power, cost, etc. Then I'll get into load balancing, congestion management, and then finally wrap up with a real-world example of what's being deployed today with Tomahawk for AI, what's available today is commercially available. So first off, on the physical interconnect, so we have a three-pronged strategy to reducing the cost, the power, and the latency for AI interconnect. First is to maximize the use of copper. So if you can use copper to interconnect the devices, that's always going to be the lowest cost, the lowest power, lowest latency. So if you look at the IEEE spec for 100 gig PAM4, it basically translates into a DAC cable reach of about 2 meters. Now with the SerDes we have, we can actually double that. So we can actually, with no retimers, no active devices from switch to switch, we can actually drive about 4 meters of passive DAC. In the cases where you can't use DAC, next step is to use optics. And what you want to do here is to minimize the cost and the power of the optics. Traditionally, people will be using the retimed optics where you'd have a DSP inside the optical modules. You may have heard at OFC this year, these linear pluggables kind of exploded onto the scene that have, much lower power, somewhat lower cost. So in the case you can't use DAC, next step is use optics. Make that optics as low cost, low power as possible. And then finally, if you want the ultimate as far as low cost, low power for the optics, we do have co-packaged optics solutions. So key thing here is that we really have a new paradigm for AI interconnect. So we're really focusing on the chip I/O. So the SerDes we have on chip includes features both for driving copper, the things you would traditionally see in a copper SerDes for like channel equalization. And we also have features that you would normally only see in an optical DSP. So some of the equalization, some of the pre-distortion, some of the telemetry that you would normally only see in an optical DSP, we also include that on chip. And that allows us to drive directly the linear pluggables and the co-packaged optics. So just waiting for the transition here. Okay, so this is real. This is something you can actually deploy today. What I've got here, this is actually the chip right now that's inside the 10-cent box. This is a Tomahawk 4. This particular switch, it has half optical I/O and then half electrical I/O. So what you see on the sides here are actually where the fibers plug into. And then the half electrical I/O are just kind of the balls in the back. So again, this is something that is shipping today. I mean, in co-packaged optics, it is real. So I'll pass this around in case anyone wants to check it out. One thing you can look at afterwards, it's a little bit heavier, is this is actually a Tomahawk 5, what we call Tomahawk 5 Bailey. And in this case here, the particular implementation, we decided in this case to make it all optical I/O. So whereas this right here is a Tomahawk 5, this is, I think, what we showed at the last network field day. This was announced last August. It's shipping in production now. So there's no optics on this. Everything is out the balls on the back. In the case of a TH5 Bailey, it's the same switch silicon. We just bolt on the optical engines around the side. So, all those pluggable optics, actually, 64 800 gig optical connectors, optical modules, all those optics are integrated into this package. Okay, in the case that you don't want to use CPO for some reason, where maybe you want to use a different type of optic, we also support what's known as LPO or linear pluggables. This has gone by various names, including linear drive, direct drive, analog, DSP-less, etc. Again, if you tuned into OFC this year, this was huge news because it was fairly disruptive. It's something we've been working on for a few years, but we actually just showed the results along with Arista and eOptolink, at OFC this year in March. So what this is just an example here of a multi-mode optical module. So inside that multi-mode optical module, you're going to have your PAM4 DSP on the driver. So if you look at the TX side, I'm not sure if the pattern shows up. So on the TX side, this actually comes out of the switch SerDes. So on the transmit side, you've got your drivers, you have your VCSELs, and that goes onto the fiber. On the receive side, you've got your photodiodes or TIAs. So with a linear pluggable, the key thing here is that you eliminate this DSP. So the switch interfaces directly to the TIA, interfaces directly to the driver. So because of that, you remove all the cost and more importantly, the power of that optical DSP. And what you're left with is the quote linear components. They're not 100% linear, but they're pretty close to linear. Basically, you put a voltage in, you get a certain amplitude of light out. On the input side, you have a certain amplitude of light, you get a certain voltage that goes back to the switch. And it varies linearly with that voltage and light amplitude. And this is being standardized. So OIF is working on a standard. It's the CEI 112 gig linear PAM4. This is actually fairly far along. This is actually started in May of 2021. So, it's not that we don't have a standard that's solidified yet, but it is fairly far along. We do have a number of optical modules that are in-house that actually implement this sort of functionality where we actually remove the DSP, and we have TAs, drivers that are tuned for linear optics. So if you look at how the different optical technologies compare, so left-hand column is standard retime pluggables. These are going to be the highest cost, the highest power. Latency is one thing that a lot of folks don't realize that you can actually get on an end-to-end link. You can add about 100 nanoseconds or more of latency just from those DSPs on either end. Link accountability is good. You've got all the tools. You got that big optical DSP with a lot of telemetry. Field serviceability is good because you can pull them out. You can swap in a new optical module. These are designed to be IEEE compliant, and definitely we're seeing already there are optical modules that are sampling that support 200 gig PAM4. If you look at, say, LPO and CPO, you'll see that the power is going to be similar. The key benefit you're going to get as far as the power savings is removing that DSP. As far as cost, the LPO, since you're removing the DSP, you do get some cost savings. But you don't have that level of integration. So again, all those optical modules, that's 51.2 terabits of optics, are integrated into this chip for the Tomahawk 5 Bailey. So certainly you're going to get a much lower cost solution with CPO. Latency is going to be similar. Again, the main latency savings here is that you're pulling out the DSP. So you're really just left with those very, very low latency linear components in the optics. Link accountability with the LPO, it's a little bit more difficult than, say, CPO or retimed optics to figure out if you have an issue along the path. Where is that issue? You don't have quite the telemetry. You don't have the tight coupling, say, with like CPO. Field serviceability with linear pluggables, you just pull out the optical module, you drop in a new one. CPO, it's all the high reliability components are integrated into the silicon. We do have a remote laser. So on the front panel, you have a field serviceable remote laser. And that remote laser is really the component. If you look at any switch system, what fails, it tends to be the laser in the optical modules by far is the most failure prone component. So that's why, our philosophy is keep, almost all the optics integrated into the chip. The things that might be failure prone, move it onto the front panel. I'd say one thing that, with LPO, as I mentioned, there is no standard yet for LPO. It's under development. It's fairly far along. But, can you be 100% IEEE compliant? I think initially what you'd probably see deployed here is bookended solutions where you have linear pluggables on either end of the link, just because the standard's not there yet. And then eventually, we do expect that you'd have the full, standard from OIF, so you can say you're OIF compliant. And the goal here is to make those optics, IEEE compliant. So what you actually see on the fiber is going to be your standard, SR, DR, FR optics. You can plug it into whatever on the front end. And then scaling to 200 gig PAM4, definitely we know we can do that. We'll have, direct drive capabilities in our switches to support 200 gig PAM4. I think right now there's a good chance we can support linear pluggables with 200 gig, but it's a bit more challenging. Basically, between the SerDes and those, TIAs and drivers, you need to have a fairly good channel. So 200 gig, if you've been following anything, what's going on with 200 gig and IEEE, 200 gig is very challenging. So that's why I'd say that, it looks promising that we can support LPO for 200 gig, but that's still under development. So, the big promise of LPO is power savings. And here we show the power for different optical technologies. And this is for an 800 gigabit per second optical module, either OSFP or QSFP DD. So left-hand side is where we are today. You have a EML for the optics. You have a 7 nanometer DSP. You have external or a discrete TIA and driver. And you'll wind up with about, roughly speaking, about 16 watts. Certainly there's some modules in the market that are a little bit lower, but in general, you wind up with about 16 watts per 800 gig. Next generation, still stay with the EMLs. Now you integrate the TIA and driver, and this is something that we also offer at Broadcom with our PHYs. So there you'll drop down to about 12 watts. Next step after that is now improve from EMLs to silicon photonics for the optics, and then go to the next step as far as going to 5 nanometer for the DSP and for the TIA and driver. And there we can get down to, about 11 watts, 10 to 11 watts. And if you look at linear drive with silicon photonics, depending on who you ask and what components are being used, you're talking about somewhere in the order of like 6.5 to 7.5, maybe as much as 8 watts for that whole module. So, depending on what you're comparing it to, you're going to wind up with at least a 33% reduction in optics power. And in general, we're seeing about 33% to 50% reduction in optics power. Okay, so just summarizing the enhanced interconnect, what we're doing to improve that physical interconnect. Again, this applies both to Jericho and applies to Tomahawk. First thing is reduce the amount of interconnect. So as we'll get into in the next section, when you say double the bandwidth of the switch, you can wind up with a 6x reduction in the number of switches. So really the first thing you want to do is high levels of integration, very high bandwidth, high radix. Next step is to maximize the use of copper. So we'll extend the reach of the copper. After that, next step is if you need to use optics, try to make those optics as low cost, low power as possible. And so we talked about the optics level, you'll save anywhere from 33 to 50%. In general, most folks are saying that it's about 50% power that you save on the optics. If you look at the system level, you're talking about 25 to 33% savings in the optics power or the total system power.
I got a quick question about the you keep saying for the copper portion, the lowest power interconnect, what's the percent ratio of that versus the optics side? What's the overall?
Oh, for the total switch power?
Yeah.
I mean, you could wind up, if you look at the whole switch box, if it was, say, like, all copper versus like an all optical solution, it could be, double the power
Okay.
with the optics.
Okay.
Yeah, I mean, that's a key thing is that there's a lot of focus on the switch silicon itself, trying to minimize the power of the switch silicon, but you don't realize that, over time that more and more power, more and more cost is moving into the optics.
Right.
And that's really been a continuing trend. And then finally, if you want to have the lowest cost, lower power optics, you move to CPO. So we do offer, I mean, the optical engines. So, we call this Tomahawk 5 Bailey. Bailey is the name of the optical engine that we have. And we actually can use that with other technologies. So we can, take a Bailey, we could drop it into, say, like a custom GPU. I mean, kind of the key thing here is that the SerDes that we have, starting off with our 5 nanometer generation, it's natively capable of supporting DAC, linear drive optics, those LPOs, and CPO. So if we decide at some point we want to take, any switch chip, any product that uses that 100 gig SerDes, and we want to add CPO to it, it's really just a packaging exercise. I mean, all the chips, natively can support, the high reach DAC, LPO, and CPO. Okay, so moving on to Tomahawk AI cluster architecture. So at the high level, you could have a very simple architecture. I think Mohan showed this earlier, where you just have, this is kind of really the most common that people would start off with, is they'd have a leaf spine architecture. And the key thing here is that the endpoints would be the ones that implement the end-to-end congestion management and the packet spraying and some of the load balancing. And then the Tomahawk devices, the Tomahawk Fabric, and what they'd offer is, they'd support that end-to-end congestion management with telemetry, with a very high bandwidth, high radix, so you can have flat topologies. It also includes adaptive routing and the support that you need for end-to-end congestion management. As we mentioned before, these endpoints could be a Broadcom NIC, it could be any other merchant silicon NIC, it could be a customer NIC. And this is actually one increasing trend we see with the hyperscalers. A lot of the hyperscalers have their own NICs. They have their own NICs, they have their own congestion management. So that's one thing that we see that, one size certainly does not fit all. There are certainly, the merchant silicon NICs, they do a very good job, in the generic case, for certain hyperscalers. I mean, they know exactly how they want to maintain their network, how they want to operate that network. They have their own congestion management. I mean, you'll see that congestion control is kind of a religion for a lot of these folks, and they say, I want to have, sender-based, receiver-based. I want to use, the TCP style, congestion management. I want to use SRD. So, it is something that, we can support all those different endpoints with the Tomahawk Fabric. So some of the features we have to support this endpoint schedule fabric are, first off, high bandwidth, high radix. So this leads to flatter topologies, significantly fewer switches, less physical interconnect, and importantly, also easier congestion control. I mean, if you had like, one switch that was interconnecting all the nodes, I mean, the switch itself, there's no, you've got like one unified buffer for all the packets. Anytime you start adding hops or switches in the network, it definitely complicates the network congestion control. Then load balancing. So we do have load-aware adaptive routing in the switch. The switch can also selectively spray traffic. So you can have spraying that starts at the endpoint. We can also do spraying from the switch to all the nodes it's connected to. Or we can selectively maintain the packet order depending on the capabilities of the NIC. So if the NIC needs to have all the packets in order, we'll just keep them in order. If the NIC can support reordering, we can do spraying to more efficiently use the links in the network. Global visibility, so we have a lot of in-band and out-of-band telemetry. And then also we have fast link failover. And I'll get into some of these on the subsequent slides. And finally, congestion management. So we do want to work with all the standard mechanisms, ECN, DCQCN, PFC, et cetera. But as mentioned before, one size definitely does not fit all. That, customers, end customers, the hyperscalers, they have a lot of teams with a lot of experience, congestion control. They know how they want to run their network. So we do have to provide a very flexible solution.
So I had a question on the high bandwidth and radix portion for flatter topologies for like a 3-class standard architecture, right? Do you guys have set of recommendations around how you are divvying up the ingress access ports to the ratio for your spines? Is there a specific configuration that you guys are doing on it?
I mean, as far as oversubscription?
Yeah.
Yeah, I think, in general, what you've seen in the past for general data center networks, there would definitely be some oversubscription, at least at the Tor node.
Right.
We're not seeing that for AI networks.
Okay, so they're going a full 1-to-1 ratio for all ingress ports to spine ratio. Which
I'd say in general, it's going to want to be in 1-to-1. And in some cases, they'll actually wind up doing some over provisioning.
Okay.
Where they'll have, so if there are failed links in the network, like some of the reports we're getting from the hyperscalers for the failure rates for optics are just unbelievable how often they fail.
Okay.
Especially when you're talking about these very, very large clusters. So I'd say the most common is that it would just be a 1-to-1 ratio. But in some cases, there are at least some experiments now with over provisioning, so that way you can more gracefully handle any link failure.
Okay, and are they doing multiple links from a given leaf to a given spine, or are they pretty much doing 400 to 800, or are they doing?
Yeah, so later in the presentation, I have an example where I can kind of go through that and show you just, how, because I think it's, it's going to you want to have, certainly multiple links where you could do some traffic spraying. In a lot of cases, they're also going to like multiple independent traffic planes, where, for example, if you had like a 400 gig, NIC for a GPU, you might split up the traffic into two, 200 gig ports coming out of that GPU and have it on totally two independent network planes.
Okay.
So I'll show one example of, actually something that a lot of some of the hyperscalers are planning to deploy that does exactly that. But yeah, in general, you're going to want to have a lot of path diversity. And I think with a lot of these networks, we can do static load balancing where you just pin a flow, onto a certain path, so you don't have to worry about reordering. But more and more commonly, you're going to see that people are going to be doing some sort of spraying. Right. And in order to do that spraying, you're going to want to have a large number of links available.
So pin from the host to the leaf, but then from the leaf spray across.
Well, just so you'd use like ECMP hashing. Okay. So basically, you just say it's not really quote pinned, but it's more just like statically defined or statically kept on a certain path, so you don't have that reordering.
Okay.
Okay, so benefits as far as high bandwidth. So we've been on this treadmill where every 18 to 24 months we're doubling the bandwidth. We've been doing this for the last 12 years. I think every generation of Tomahawk, we say like, who's going to need to have 6.4T? Who's going to need to have 12.8T? That's too much bandwidth. Every generation we've gone through that discussion. And every generation, especially now with AI, we're seeing that, they will take as much bandwidth as we could throw at the problem. We could have, petabits per switch and it will be used because there's like so much data that needs to be transferred. And Tomahawk 5, this is shipping in production. I think we actually announced that this was production qual complete in Q1 of this year. So it's actually possible to deploy networks today with Tomahawk 5. And there's no other switch on the network. There have been a couple others that have been announced at 51.2T, at least Ethernet switches, but they're just starting to sample. So we were actually deployable in production before those other switches even started to sample. Okay, so Tomahawk 5. So last network field day went through a lot of the high-level features. Just focus on a couple things here. So again, we do support 800 GigE ports. Today what you'll see is a lot of the GPUs are more on the order of like 200 gig, moving to 400 gig. But certainly there is a movement towards 800 gig and even higher bandwidths in the future. So we do have native 800 GigE support. This is a monolithic implementation. Anytime you can stay monolithic, it's going to be better as far as power, as far as latency. We do have features that accelerate the AI workloads. So I'll get into cognitive routing that provides very good load balancing in the network. And as mentioned before, we put a lot of effort into that low cost, low power, physical connectivity. So most of this presentation, all presentations today are focusing on the switches. We do support end-to-end solutions. For example, we do have the Thor 200 gig NIC that is shipping in production. So this can support, 200 GigE ports or a single 200 GigE port with 50 gig SerDes. This has hardware support for Rocky, very low power, so 16 watts, all in for the NIC card. And we do have advanced features such as, silicon root of trust, multi-host, multi-root. So, we do have, and I'll get into later, there's actually, if you look, we have a suite of silicon, and software to support end-to-end solutions for AI. Okay, so getting into benefits of bandwidth. If you've been around this industry for a while, you've probably seen something similar to this. So let's say, for example, you had a cluster of 256 GPUs that had a 200 GigE Ethernet interface. That winds up being 51.2 T of bandwidth total. So if you wanted to have 51.2 T of bandwidth, you can drop in, on the right-hand side, Tomahawk 5. Alternatively, if you wanted to do it with a 25.6 T switch, which is, aside from Tomahawk 5, that's the only thing that's available on the market now. You'd actually need to have, 6 switches. So you have 12.8 T per switch that's facing the front panel. And then the additional 12.8 T faces just the interconnect on the back end. So if you look at that group of switches, you actually have a total of 153 terabits per second of switching capacity. So you've got 3x of switching capacity, 6x the number of devices. And perhaps even more importantly, you have 153 terabits of interconnect. And usually that's going to be optical interconnect. And if you look at, that 16 watts per 800 gig, you're talking about 3,000 watts here just to power the interconnect. And if you go to a single switch, that all goes away. So that's why, this doubling of bandwidth, like staying on something there, with Ethernet especially, where you can have the highest bandwidth, is super critical as far as minimizing costs, latency, and power.
So one question, why the 4-port on the 200 gig Thor? In the advanced options, you said there's 1, 2, and 4.
Yeah, some people want to use, like 4 by 50 gigs, so they'd actually have, 4 50 gig ports coming out of that. Oh, okay. So you might have that for just path diversity. Okay. Mm-hmm. Yeah. Okay, and just a bit more detail. So here's an example again that, a lot of the common, high performance GPUs now are 200 GigE, moving to 400 GigE in the future. Tomahawk 5, you can connect, 256 of those. So that one node, so if you look at this one section here, we got 256 nodes at 200 gig can be connected with one switch. You need to have, 6 switches and 2 tiers for any competing solution. If you wanted to go, say, to a fairly large GPU cluster, 32K nodes, that would be 384 Tomahawk 5s. That's just in 2 tiers. Any competing solution, you'd have 3x or more than 3x the number of switches, and that would have to be done in 3 tiers. So again, that's why we focus so much on getting to the next bandwidth level, the next radix level, because it's so powerful as far as reducing the cost, the complexity, and the power. Okay, so getting into the load balancing, congestion management. Again, what we need to do to support this end-to-end endpoint scheduled fabric. So we have a suite of capabilities we call cognitive routing. This will improve the routing for all traffic types, but is especially impactful for AI flows. We do support with this cognitive routing suite, all common topologies. I'd say in general, people really tend to go to the fat tree or closed networks. There are some cases, especially for more like HPC applications, that people would go to Taurus, Dragonfly, etc. So we do support that. I'd say most of the hyperscalers really are going to stick with the closed networks, however. And the goal of this suite is to improve the network utilization and lower the tail latency. So during the last network field day, we talked a bit about this. I'll go into a little bit more detail on some of these features. But in the cognitive routing suite, first feature is global load balancing. You've probably heard of dynamic load balancing in the past, where for every packet, you'll see, what is the loading on the different egress ports that packet or that flow could go onto. And then depending on the queue size and the port loading, you'll try to steer that packet, steer that flow onto the most lightly loaded link. With global load balancing, we'll actually take into account the congestion information downstream and use that to decide on the best global path through the network. Second feature that I'll go into a bit more detail is reactive path rebalancing. Now, as Mohan mentioned, the AI communication characteristics are fairly unique that you wind up having a lot of very large flows that hit the network simultaneously. So, you don't have anything to say, okay, this link here is more lightly loaded than this one because, the network is lightly loaded before all that communication starts. So it might happen that you wind up pinning or putting two very long-lived flows onto the same link. So what we do here is for every packet, we'll take a look, say, is there a better path for that flow or that flowlet? And then in a probabilistic fashion, potentially steer it onto a better path through the network. We have fast link failover. So with this switch, in less than 500 nanoseconds, we can automatically steer traffic around failed links. And then final feature in this cognitive routing suite is DCN, or drop congestion notification. This is also known as trimming. And what we do here is as a packet flows through the network, if it hits a switch that's got a full queue, rather than just dropping the packet and then waiting for the transport to say timeout and then retransmit it, what we'll do is we'll take the packet, we'll just grab the header, we'll tack on some metadata, and then we'll forward that to the destination. So you get a very fast response. You wind up having like very shallow queue depths. You have a very fast notification of when the packet was dropped and why it was dropped.
Chris Cummings here with a question. With all of these routing features, are these all in-band or inline protocols that are part of the fabric, or are they more of a centralized controller kind of making these decisions? What's the actual pathway for all of this?
Yeah, so for all of these, it's going to be in the fabric. So for example, global load balancing, there are two components. There's one component that is in actually the packet processing pipeline that in real time on a packet by packet basis will determine where to steer that packet. The congestion information that comes from a remote switch, that's also in fabric, where we'll have one switch with an embedded application send the congestion information to an upstream switch, and that'll be used to program the tables in the packet processing pipeline. So that's also in fabric. The other ones, reactive path rebalancing, that is something that is native in hardware on the switch. Fast link failover, that's also hardware on the switch. And then DCN, so that mechanism is in hardware, but you're taking that data plane packet, basically effectively converting it into a control plane packet that would go to your receiver, and then it would usually be the sender and the receiver, something on either end, and the endpoints that would then determine how to do the congestion management.
Okay, cool, thank you. And then are these all interoperable with other vendors? I know with Broadcom's position, it's kind of unique because you're not necessarily selling your own switches as much, but are these like standards-based things that are interoperable, or are they more of you have to be all in on this fabric and it has to all be the same?
I'd say for the global load balancing right now, those messages that we're sending back and forth, that is proprietary. It is an embedded app that we have. It's something we may open up, but right now it is proprietary messages. You can still use that, that same hardware without that remote congestion information. You just use the dynamic load balancing. That's something that's in one switch, and it really just looks at the local switch net metrics. So that doesn't, that is completely interoperable. There's no dependency on the rest of the network. DCN. So what we have right now, that is a proprietary format we have with that, but you may have heard of the Ultra Ethernet Consortium, and Mohan will be covering that later. This is something that sort of packet spraying and the ability to use packet spraying effectively is something we're looking into UEC. So this may become a standard. Right now it's proprietary, but it is something we are pushing to be a standard. Okay, thanks, Chris. Okay, so global load balancing. Talked about this a little bit last time, but I'll kind of rehash a bit what we discussed. The key thing here is that the local decision for the path is not always going to be optimal as far as balancing throughout the network. What we show here is an example of if you had a packet going from Tor 1.1 to Tor 1.6. As you traverse up the network to the top tier, you have multiple paths that you can choose to that top tier. By definition, in a closed network, however, once you get to that top tier, you only have one path down to the destination. So for example, if you're going to say you had from 1.1 to 3.1, if you followed that path, then you'd only have that congested, that red path down to the destination Tor. So really what you'd like to have is when you're doing the decision on 1.1 where to steer the traffic, you'd like to get some information that, oh, by the way, from 3.3 downward, that's an uncongested link. So now I can follow a path up the network, so that way I can have that uncongested path, downward to the, to the destination Tor. So reactive path rebalancing. So we really haven't talked too much about this before, but what this does is for every packet, so this is in hardware, on a packet by packet basis, when the switch is asked to forward a packet, we'll first say, is this part of an active flowlet? And if it isn't, then we will assign a path using dynamic load balancing, or it could be ECMP, hashing, it could be global load balancing. And in the case that this is part of an active flowlet, we'll say, is this current path assignment good? So we look at the link quality, the egress link quality. We can look at the global path and say, is the path assignment good? Is it lightly loaded? Or alternatively, is there a better path, a significantly better path we could put this packet onto? So in the case that the path assignment is good, it's okay, great, we'll just keep the current path. In the case where the current path assignment is not good, or we see that there is a significantly better path, in a probabilistic fashion, we can reassign that flow onto a different path. Now, we don't want to do this, and this is the case that if you had to maintain packet ordering, this is where this comes in. So in that case, you don't want to do this on every flow. You don't want the network thrashing. So it's really more a statistical probabilistic measure where you say that if the probability has not been met, so I don't want to move this path or move paths around too quickly, it's like, no, I'll just keep the current path assignment, even though there is one that might be slightly better. But in the case that you say, yes, I've met this probability, I do want to steer this onto a different path, I'll now choose a new path with GLB or DLB. So in this case here, if you're choosing a new path, you might wind up having a different delay through the network. So you might wind up with packets out of order, but just having that momentary glitch is going to be much better than having two very long-lived flows that might be hundreds of megabytes that are continually and for long-term congested on links. And then DCN, or drop congestion notification, also known as packet trimming. What we do here is we will, at the endpoints, we'll encapsulate the packets with a DCN header. The endpoints will also implement the end-to-end congestion control. And the transit switches would update the DCN header with telemetry. So there's a fixed length header. So for example, it can include like the residence time, it can include the queue length. And then in the case where the packet would be dropped, again, rather than just dropping the packet silently, we will trim the packet, tack on some metadata, then send that to the destination in a high priority queue. So what we show here is, the top part is the no loss scenario, where the host, puts the, so the endpoint puts the, it encapsulates the packet with a DCN header. As that flows through the network, we'll tack on some metadata. And so the end host in the no loss scenario now has some additional metadata that was collected along the path. In the case where you would have dropped the packet due to congestion, you take it, you trim it, put metadata on it, place it in a high priority queue, and then forward it on to the destination. So this works with, in particular, with different scheduling mechanisms. But at Broadcom, we also offer what we call the Edge Queue datagram service. This is actually came out of a company called Correct Networks that we acquired about a year ago. And the idea here, as per the name, is that we want this to be edge queued. So you move the queues onto the edges of the network. Try to minimize the queuing within the network. So key thing here is that this sits underneath your host transport. So it provides services underneath the host transport. That transport could be TCP, could be Rocky, etc. And then we'll leverage whatever capabilities you have in the network. So for example, if you have that DCN or packet trimming, we can leverage that, have more responsive congestion control. So again, this is a very flexible framework. So it could be different host transports, leverage different network capabilities. And then EQDS will schedule packets onto the network. It will spray it onto all the paths. It'll reorder the packets at the destination. And if a packet's dropped, it'll have that packet retransmitted. So this is, software that we have. This is something that we are supporting or will be supporting throughout our product lines. And this is something that, for customers that are doing their own NICs, we can also offer this, as source code to them so they can actually implement that, in their hardware or on an embedded processor.
Otherwise, you're just doing this on the leaf, right?
So on the leaf, so this sort of functionality where you're doing the spraying, the reordering, that will be done on the leaf in the Jericho solution. The Tomahawk doesn't include that functionality. So by definition, Tomahawk, this would have to be done at the endpoints.
Right.
Okay, just to give you an example of how powerful this is. So EQDS, again, sprays packets across all the links. Standard protocols like TCP, Rocky will do like a static ECMP hash. What we did here is a simulation where we have 432 endpoints with an all-to-all traffic pattern, 2 megabyte flows, and we show this is what you would get if you just use static, ECMP hashing for Rocky. So you wind up with about 1,000 microseconds for the transfer time for the flow completion time of the last flow. With EQDS, with the packet spraying, and again, there's a schedule fabric with EQDS scheduling, you get almost, near ideal behavior in the network. You wind up with like 1/5 of the total transmission time for those flows. So this is, really the reason that we, acquired Correct Networks, because this packet trimming, I think it was in 2016 that it first came out. There's a SIGCOMM paper that won like the best in show, paper. So it's been around for a while. It's fairly mature. It provides really good, traffic scheduling. Okay, so just get into some concrete examples of how this all ties together. So first off, what is the silicon that Broadcom provides for AI? So in a case where you're using GPUs and CPUs, we provide NICs, we provide PCI switches to tie together the CPUs, the GPUs, and of course we provide the switches. We do also work with a lot of customers on custom ASICs. So a lot of custom training ASICs that are already being deployed in very high volumes. And in those cases, we provide PCI switches, the NICs, we provide the custom ASIC surfaces. We also provide NIC chiplets. So if you wanted to have a custom ASIC, but you didn't want to worry about the networking portion, we'll provide a chiplet that you can include with your training or your inference ASIC. And if needed, we also have, again, those optical engines, the co-packaged optics that you can include on chip.
Question here, are any of those living on the NIC, or are they something else that'd be living on the rest of the hardware?
Any of these features living on the NIC, or as far as like the CPU?
Yeah. The ASICs, the NIC chiplets, for example, would those actually be on the NIC itself, or would you have to access them? It looks like maybe over PCIe as a different card or something else you'd install in the system.
Well, in this case here, we're actually showing that ASIC, that red box with the ASIC, that would actually be like one chip. So you'd actually have a chiplet that'd be sitting native, next to. So you'd have all your inferencing engines, and then there are different interfaces you can have in between that inference engine and the NIC chip. So it could be PCIe, it could just be like a wide parallel interface, but it would all be just integrated onto one chip.
Right, but I guess my question that I'm not phrasing super well, sorry, is for actual packets coming in that I would need to process, potentially through this ASIC. Would those go straight from the NIC to the ASIC, or do they have to be brokered by the CPU in this scenario?
Oh no, so you could have, it could just go straight from the network, through that NIC chiplet, so it doesn't have to go through the CPU. So yeah, that NIC interface could be directly to the CPU, and then you transfer through PCIe. Alternatively, it's just a native Ethernet interface that you have on that GPU.
Got it. That makes sense. So it's like a port on the back of it per se, not a separate piece of hardware. Yeah. Got it. Okay.
Yeah, and what we're seeing is that a lot of these ASICs, 200 gig, 400 gig interfaces are great, but we see some ASICs that want to have, many terabits of networking interface. So in those cases, you probably wouldn't want to go through, a NIC. You'd actually want to have a native Ethernet interface, on chip. It's what you've heard before about bandwidth, 200 gig, 400 gig, it's going out. It's many terabits that you want to have even for one training ASIC.
But I guess the question then becomes, GPUs, especially from companies like NVIDIA, have a native interface in them because they're running InfiniBand directly to the GPU to bypass the stack in order for this to happen. So is that kind of what you guys are trying to get to, is that capability of running directly into the GPU to bypass the stack completely to reduce latency?
Yeah, and you can do that. I mean, you can also just use RDMA right now, where you're bypassing the stack going directly to memory.
Right.
In this case here, it's actually going to be a bit more direct path, yes, because the CPU is not involved at all. So there is no stack. It's basically, you've got the native, NIC interface sitting right next to your training ASIC, just dumping the data to and from the native memory for that ASIC. So you could, for example, have an ASIC that's got HBM, and then you'd have the NIC interfacing through the ASIC, directly to that HBM.
And the NIC isn't adding significant nanoseconds of overhead to dump everything directly into the GPU memory? Because I know that's one of InfiniBand's things that they tell you is, even adding 10 nanoseconds of latency can be a problem, but it's also, we're dealing with Ethernet here.
Yeah, I mean, this is going to be some added latency, but, this added 10 nanoseconds of latency, that really is more important for HPC. For AI, it's all about bandwidth.
Right, because you still have to wait until the last GPU in the node finishes the task before it can return the results of the entire calculation. So, you're still blocking at that point.
Yeah, and also, the message sizes are tremendous. I mean, you're talking about hundreds of megabytes. Yeah. So you think about transfer hundreds of megabytes is going to take you, tens, hundreds of microseconds. And if you save 10 nanoseconds on that, it's much less important than be able to have this huge pipe that puts the data in as quickly as possible. So yeah, I'd say that that kind of 10 nanosecond range is something that maybe for HPC applications is important. It's really it's not so much about latency for AI. It's more about just the raw throughput and just using your links, getting as much bandwidth as possible.
But again, that speaks to the fact that InfiniBand was originally developed for HPC Interconnect, and now it's being adapted to AI. Yeah. And I think that's mostly because people already had it. And we're just going to reuse it since we have direct interface into the GPUs, which are running the calculations anyway. And this is an effort to re-engineer Ethernet to be more performant towards that ultimate end goal.
Yeah, and I think we've even seen today, both with the Jericho solution and with the Tomahawk solution, we've done head-to-head comparison tests with InfiniBand, even ignoring the fact that we have higher port speeds and higher bandwidth and higher radix. At the same port speed, at the same radix, we outperform InfiniBand. And then if you take into account the fact that we have, double the port speed, double the bandwidth, you wind up having significantly better performance. So yeah, I think InfiniBand is kind of, it's been in HPC, it's kind of migrated to AI because it's been in those, high performance networks, but it doesn't provide the best performance. And, as Mohan will get into, and we see that there's a lot of momentum right now behind improving Ethernet, specifically for AI. Okay, and just to give you a concrete example of how this is being deployed today. So, what we see here, this is an example architecture where the GPUs have two 200 GigE interfaces per GPU. On the uplinks within the network, they use 400 GigE, so that way you have just a bit better utilization of the optics. It's a little bit easier for load balancing. And what they've done in this case here, and this is something that is in the process of being deployed at some major hyperscalers, is that per pod they'd have 1,000 GPUs. Each of the GPUs has 2 networking planes, so you'd have 1,000 200 GigE ports per pod, 16 Tomahawk 5s per pod, so you've got almost a petabit of networking per pod. And so anything in purple you see here is going to be one networking plane. Anything in yellow is the other plane. And then finally, you might tie those two planes together at a top tier. And just to show, this is something that is, this is real, this is something that's available today. So, one particular example that we have is with Arista. This is and actually, if you want to get more information, there's a huge amount of data. We got YouTube videos, we got white papers, etc., that are available. And this is something that's deployable today. There's a complete end-to-end solution with the NICs, with the switches, and with the software.